So our next presenter is Pedro Bertinelli, and the title is Trans-Neptunian Science with the Dark Energy Survey.
Hi everyone, I want to first thank the organizers for inviting me to do this talk, and also congratulate them for doing an excellent job in basically having most of the invited speakers be early career people, so excellent job. Let's keep doing this as a field, that's a great practice. So let me talk a little bit about probably the weirdest TNO survey that you've heard about, the Dark Energy Survey. So as the name says, this is not a survey meant to find TNOs. This is purely something made to measure dark energy. And I think most of us, except for like one or two people in the room, don't actually care about dark energy. We care about planetary science. So let me talk a little bit about why we're doing this and how we actually were able to transform this into a very successful TNO survey. So the DES was a project that took images between 2013 and 2019 using the One telescope in the Dark Energy camera. And the goal of the project is essentially to map galaxies. And to do this, we covered roughly 1 inch of the sky in high-output filters. We went to very high Q2 latitudes. And our cadence was basically taking 1 image every 2 weeks for each location in the sky. You've seen a lot of talks this morning, you'll see some later today, where people basically take a bunch of images so you can see the motion of the object. So this is basically that. So let me give you an overview of the discovery process and how we were actually able to find objects in the DES survey. So we started with our catalog of single detections. We identified transients and went ahead and linked them by finding parent triplets, spending 20 million CPU hours going to orbits and then confirming these detections. So let me see if I can get this movie to work. That will kind of illustrate the process a little bit. So we start with 4 single images. Basically, we take an image of the sky, we have a bunch of them, and because we have a bunch of images, we can essentially see the motion of an object. We can see basically if an object disappears. It will then go ahead and come back a few weeks later, and do this several times. And by doing this, we can start tracing the orbits of these objects. We go back a few years later, that's when we're kind of sure that we have a TNO because we're seeing this in multiple years of data, so this is the real solar system source. And then this is the pattern that I imagine most of you are familiar with for this thing's on the sky. This is the DES footprint, and this is where we found essentially all of our objects. So let me give you a little bit more detail. And I'll skip the last part. I think everyone here knows how the solar system works. So you can see. So let me give you a little bit more detail into how we did these things. So we started our catalog of individual detections. After doing this, we did this idea of positional matching between both our single detections and our coads. If you look here at the images, the image on the left shows you one individual image. The image on the right shows a coad, so basically a stack of images. And if you have a moving object, when we go back years later, this thing disappears, so you're stacking your source with the background. And this is a very good way of identifying this moving object. Basically, there's nothing there when you go back, so hey, good, it's something moving. So we started with a catalog of 10 to the 10 singular reflections, and we were left with something like 10 to the 8 transients. And so we can ask ourselves, does this make sense as a process? Are we actually finding what we should find here? And the answer is yes. So here's the DES footprint. Each dot is one exposure in R band, and the color here tells you how many things we found in this exposure, how many kinds of moving objects. And you can see very clearly that there's an overdensity of transients on the acoustic plane. You see the asteroid belt. Asteroids are indistinguishable from TNOs at this stage. So this is basically the best we can possibly do to find things in a data set like this. Then we need to actually connect these things into orbits. So the way we're doing this, we're asking the question, given this 100 million detections, which 10 or so belong to one TNO? So which 10 or so come from the same object, and we can actually go ahead and trace an orbit for these objects. You can imagine that this is a very big combinatorial problem. Because we're fitting orbits, we ideally need 3 detections. So the naive way of doing this would be to basically combine everything in single three combinations, and then that's 10 to the 8 cube, which is an impossible number, and we don't want that. So we have to be a little bit smarter about this. And the way we did this was essentially by positing that we knew the distance of the object. If you do this, then you can reduce your cover space by a very significant factor, and then your process becomes a lot easier. So we went from 10 to 8 transients to 10 to 13 pairs, 10 to 12 triplets. The 10 to 12 triplets are the ones that we can actually fit in orbit. So go ahead and measure, see if this thing shows up in every other image. This was incredibly computationally expensive, so 15 to 20 million CPU hours. That is a lot of compute time. Thankfully, people at Formula were not so mad at us for using this, so we were able to actually do this already. And the problem here is that we could only target things further than 20 nanometer. Going closer, you have basically another factor of 10 in CPU time, so this is something that we could do. Then, all right, so we have the 7 actions or so that belong to an object. How can we actually be sure that this comes from a real TNO? DS has measured sky, basically, every measured sky about 15 times over the 5 years of survey. And many objects, they're right at the detection threshold. So what happens is that in many of the images that we took of these objects, the objects too faint to be detected. But that doesn't mean there's no signal there. We have here both images that are with detections. Those are crosshairs in red, and the images where the object is not detected, crosshairs in blue. And what happens is, if we stack just the non-detection images, these are completely statistically independent. If there is a real object, this is some signal popping up, and then you can be sure that you have something going on there. On the other hand, if you have, for example, 7 random points that look like they fit in a perfect orbit, if you do the same process, the object doesn't stack. Well, you can stack, but then you're not seeing signatures. So that's kind of a very stringent data that we have something real in our data. So, after spending all this CPU time, we were very successful. We found a grand total of 114 TNOs. This is comparable to OSIS, for example. It is the largest survey out there today. And we had some conversation this morning about trying to find things at very high quick latitudes. Well, we can take a look here that we have basically 0 detections past 50 or so degrees of quick latitude. We went almost all the way down to the subcryptic pole. You could find objects there, but they're simply not there. And also, we were complete to about magnitude 23.7 in our band, and we only see basically objects at 60, even though we would be able to see things far farther than that. So let's basically say that they're not made distant objects. Sorry. So here is the usual simulation axis, eccentricity inclination diagram that I think most of you are used to seeing. You can see that there's a lot going on here. Lots of objects at high inclination, lots of objects at high perihelion. And let me give you a little bit of the numbers that we have here. So we have this 800 and so objects. 400 are classical, so those are total hot classicals. We have 150 detached objects. I think this is the largest compilation of detached objects to date, which is not a surprise because we're looking for things at high inclination. So that's how we see these things. We have all sorts of interesting resonances going all the way down to the 25 to 3 and a bunch of scattering objects as well. So let me tell you very quickly about some of the interesting objects that we found in our data set. So we have objects in very distant low eccentricity orbits. We have things all the way down, just the resonances. We have 16 extreme TNOs. These are the ones that matter for the planetary hypothesis, and I'll talk to you a little bit more about that later on. We have this object with 55 perihelion that is in the 6 to 1 resonance, so it's a candidate to 6 to 1 resonance. And we also have an object here that is very crude. This is being a low-power orbit with a similar axis of 20,000 AU with eccentricity of essentially 1. So let me tell you a little bit about these objects, and then we can go back to talking about TNOs. So we found this thing, 2014, we went to 7.1. That's something that we were not expecting to find. We were only thinking about TNOs, so this is an object that kind of surprises us a little bit. So this has a semi-major axis of 20,000 AU, so that's very clearly an object coming from the Oort cloud. And an absolute magnitude of about 8, so bigger albedo, that gives you 155 kilometers in diameter. So that's kind of like a TNO size. So sure, we found a TNO with a orbit, that's fine. It was not so surprising for us because we weren't thinking too hard about this object. And the first DES images that we have in this object are about 29 EU, and it's very, very consistent with the point source in these images. After we submitted this object to the Microflight Center, very quickly, someone else published an analysis using test data, and it was very clear that this object was active. In these test images, they are from 2018. That's basically around the same time we have these DES images. So it made it very clear to us that we were missing something. This is obviously a point source. That's obviously an active object. What are we missing here? So then we went back and looked into the images of this object again, and we realized that we were only trying to search for coma very concentrated on the nucleus. But if we redid this analysis using basically a very large scale, we could very clearly see both a tail and a coma in this object. So there's a very clear detection of this coma and tail closer to 26 AU. Basically, we're seeing this coma turn on and measuring activity. And the surface brightness, I read back these numbers, we have detection of a coma of about 30 metrics per second squared. If you turn this into very exotic units, this is 0.004 electrons per second per pixel measured on the image, which is incredibly faint, and it's phenomenal that we're able to detect it with our data set. And this is very clearly a work-called comment, so we can ask a little bit about the dynamics of this object. So we went ahead and did some integrations. Sorry, I completely forgot what I was talking about. We did some iterations of the orbit of this object, and the problem with the Oort cloud is that we also have to care about things like galactic tides and passing stars. And we were able to determine that the previous period for this object was between 17 and 21 EU. The current period is 11 EU, so it's basically the closest that we're seeing to this object. So in other words, there's essentially a lot of fresh material that is being exposed to the sun for the first time. This is kind of interesting. You're going to get to see a lot of interesting stuff for this object. And I think Bryce is going to talk to us about that on Friday in his talk. But sure, why is this a big deal? Why do we actually care about this object? Why is this something interesting that I'm talking about here? I told you that this is a TNO-sized comet, and it turns out that basically the last time we saw a TNO-sized comet was 300 years ago. There's this comet discovered in 1729 that has a diameter of like 100 kilometers, measured by eye, because we didn't have things like DECAM back then. So we basically beat a 300-year-old record in our comet discovery. And considering this is a project meant to do dark energy, we were actually very successful for making most of these science. So let me go back to TNOs and talk to you a little bit about the statistical properties of our sample. First, we can, for example, compare classical objects. For a very long time, basically the state of the art for classical distributions was this CFAPS model. This was published, if I'm not mistaken, in 2011. And then I know that JJ has this new model, but as soon as he publishes, we're going to try to break this data as well. That describes the Kuiper belt as essentially a combination of three components. We have the hot, the stirred, and the kernel components basically going from 40 to 47 AU range. And this is a completely independent data set, so this is a very interesting validation of this model. And what we have is that we have a very clear disagreement between your inclination distribution with the CFAPS model and DES data. And so we ask ourselves, all right, is there a way that we can essentially fix the inclination distribution for this CFAPS model, reweight things so that it would match the DES data? And the answer once again is no. So in other words, our inclination distribution is completely incompatible with the CFAPS model. And considering that we're going to very high values, it's kind of not a surprise that we're seeing different things here. There's also this idea of the point of hypothesis. We heard Wes talk about this earlier this morning. So with DES, we were able to find a bunch of these objects. So we can actually ask ourselves this question. So we actually have three different analyses published on this. Two by me, one by Kevin, who's sitting there. And we use completely different methodologies. We use only DES data in two of our analysis, can we combine DAS data with muscles and the survey of shopping in Trujillo, and completely different models for what the scatters would look like, completely different analysis, but we got a very consistent answer. This clustering that we should be seeing for the quantum hypothesis doesn't show in our data. So in other words, one way of putting this is that our data does not require our objects to be clustered to be explained. So they're essentially consistent with being uniformly distributed in the gravity models. Of course, this is a small sample size. We have 16 objects. If you want to search for objects that are more, we use objects that are more detached, it's a smaller number. So there's still some small number statistics thing here that may prove us wrong, but this is kind of basically a dandy step in the quantum hypothesis. And of course, who we have found by now? We surveyed a good chunk of the sky. So maybe, and we were trying to find things up to 2,000 EU. So maybe it was there, and we could have found. And by itself, DAS accounts for essentially 11% of the quantum parameter space. Right now, with N-stars and ZTF, we're about 80% of the parameter space that has been covered by surveys, and we're still doing that. Which is kind of disappointing, but maybe it's not. I guess that was the point of my soft history. You're one of us as people. Another interesting thing that we were able to do with our data is this idea of resonant dropouts. These are objects that people have been discussing in the literature for a few years now, that basically it seems like there is a preference for hybrid hidden TNOs to be found sunward, so closer in closer major, smaller major axis than some high order mean motion distances. Also, as a result of this, and once again, here's an independent sample, so we might as well try this again. And we combine data from a bunch of different higher order resistances, and we have a very strong statistical significance detection of this point, which is kind of interesting. It means that basically this is a real fact, and there are things that we do about this. Another interesting thing that we were able to do for the detached population is that because this is a very large sample size, we were able to actually do some interesting dynamical modeling. So this is a model from David Pizzorni that used basically just the known solar system, and it was not able in any way to reproduce the radial profile of the detached population. That's the image on left here. However, if we start the solar system and if we have a close encounter with the star early on, this will increase the radial distribution of the detached objects. And it looks like it matches the data pretty well. So we're positing here that one way of doing this is if you have encounter with an M-bar star early on in this solar system, and that kind of reduces for detached population. This might not be the only solution, but it is one solution, so that's an interesting thing. An interesting thing about DAS is that we have a lot of photography for all of our objects. And because we can target our objects, we're all seeing serendipitously, we have to do a little bit harder than the typical survey to measure fluxes. So we came up with this technique called C-model photometry. This is something that has been used for years now in the supernova community. And the idea is that this allows you to get optimal flux measurements even when you have something like a background source. So if you look at the image on the bottom there, that's one of our TLs, don't mess with the bottom, I don't know what it is, exactly the same. It's very clear on top of a galaxy or a star or something like that. But then we can do this modeling, that is the next panel, that is trying to both fit the point source, and it's using all other images that we have of the in the sky to fit the background as well. And when we do this, we can essentially deblend the two sources, and we have an optimal measurement of the fluxes. And this has an added bonus that it allows us to do quartz photometry of TNLs that are below the collection limits of the images. So in other words, we can measure fluxes on the signal fibers too, which is something that matters, for example, for the background image. And this idea of the scene modeling photometry can be extended to fit, instead of just one point source, you can try to fit two at the same time. we know that many TNOs are binaries, so this is essentially one way of detecting binary TNOs. So this is what we're doing here. You can see very clearly on the TNO on the top that you have your residuals for the photometry. They have a very clear dipole pattern that is indicative of if you have 2 point sources. But if you fix or with 2 point sources, you have perfect residuals. So you can study essentially the statistical improvement in your model as a way of discovering binaries. So we applied this to the 30,000 photometric measurements that we had. We actually just found 2 binaries. But these are white binaries, so these are red objects in the And sorry, I don't talk. This is killing me. So every TNO that we have from DES has between 30 and 50 measurements in those 5 different measurements array. So what we can do here is try to measure these colors. And a problem here is that basically we're measuring TNOs at random times. So if we just try to take, for example, a mean color, this is going to be enough because of the TNO is rotating. We're getting into different points of its rotation, so it will completely screw up our colors. So what we're doing here is trying to account for this by doing some probabilistic modeling in the fluxes of our TNOs. So we know that every TNO measurement is at a random phase, so we can take this into account, and instead of just trying to measure the fluxes of the objects, we measure the flux in the light curve amplitude. This is basically the bottom plot showing this here. And we get then for free some measurement of the variability of the object. And this is kind of like a fully probabilistic approach, and allows us to do some interesting science later on. I'll talk in a few slides. And just to demonstrate how good the data is, we did this analysis for Ares, the dwarf planet. Ares was the brightest TNO per sample. This means that we're able to do basically the highest precision science. And here is phase folding for the Ares light curve with a very good detection of 15 millimag amplitude light curve variability. So if you look at the plot here, you can see the error bars are on the order of 5 millimag or even less for each point. And combining the data from DES with Gaia, HST, and Palomar over 6 years with a mix of high cadence and sparse data, we followed this light curve to find its period, the light curve period for Ares to be consistent with this Zodiac, which is its moon, which is basically the synchronous idea favors the giant impact origin for this Zodiac. And we can also use this to constrain light curve distributions. So we came up with this functional family called the data distribution. This is a very versatile 2-parameter family. The 2 parameters they care about are basically the mean of the distribution and how sharp it falls, so basically how quickly it goes from 0 to its peak. And by doing this, we were able to slice our data in lots of physically motivated ways, both in size and dynamics, and we have some pretty interesting results. So here, the x-axis is what you should be caring about. That's the mean light curve amplitude. And each one of these posterior distributions, they correspond to one different subpopulation. So we start with the big objects. They are clearly less variable than other TNO populations. This is kind of expected. The bigger objects, they're rounder, so it's not surprising that we've seen that. We also have the cone classicals, or the more variable population that we have, which is consistent with this high fraction of contact binaries or simply more elliptical objects. That's also something that was kind of expected, but this is a very good demonstration of this effect. But then you get some pretty interesting stuff, pretty confusing and interesting results. For example, we have the scattering and the detached families. They have similar dynamical origins, they have similar color fractions, but they have different, decisively in the statistical sense, light curve amplitude distributions. So we still don't really know how to interpret that, but that's an interesting result. And the rest of the objects, they're consistently basically being a mix of hot classicals and detached objects. And every TNO from DES has very well measured generalized photometry, plus multi-year data, plus light curve amplitudes, plus whatever students score devices. So you can think of this basically as a precursor data set to LSST. And this is the largest uniform catalog of TNO powers out there. So this is a figure that I will not talk to you about because you're going to hear me talk about this on Thursday. But this is what happens when you have your usual centimeter axis eccentricity inclination diagram, but the color of each point represents the TNO color. So there's clearly a lot of structure in this parameter space. There's lots of interesting things to be studied. So stay tuned for Larry's talk on Thursday for some more discussion about this. And just one other point before I summarize. Basically, everything that we have done with DES is public. All of our data is public. Our catalogs, our individual measurements, pretty much every single line of software I've written is public. If it's not, ask me and I'll make it. This is something that we as the community should be better at. And well, this is us trying to do this. So thank you, and I'm happy to take any questions.
Any questions for Pedro?
So your light curve amplitude distribution for the hot classicals, yeah, what's up with that?
What do you mean, what's up with that?
It's like a delta function.
Oh yeah, it is a delta function because it's, well, that's the largest population, so it's a better constraint. I think when we computed this posteriors, we didn't have enough bits to actually fully model the distribution of this.
Okay, so it's just narrow.
Yeah.
Okay.
It's basically a well measured.
Yeah. Okay.
That's a good act.
Hi, Joshua from Utah. Really cool presentation. One thing that I just noticed that I thought was interesting was getting the period. How did you do that for getting the period of, the period that was 15 days?
So for the typical DS, we do not have a period. Because we have 30 measurements over 6 years of data, it's very hard to do inversion in 100 periods. So that's why we do this probabilistic modeling where we just measure the line. For errors or analysis, basically just your standard periodic analysis to Michelle has a question.
Thanks, Pedro. This is amazing amount of work. One of the things that I particularly noticed with the data set in your discussion of the absence of the high inclination population. This has always come across from the published work as being a key predictor of something large and distant in the solar system, right? Is the presence of a mass like that leads to high inclination centaurs, leads to a large population of high inclination detached objects. Could you comment on that absence in the data set?
Yeah, that's a great question. So part of it is lots of these objects that have lower perihelion. So they have perihelion closer to 20, 25 AU. That's a population that will miss anyway. Because we usually see this thing where they're perihelion and we're only trying to find things, we're only capable of finding things farther than 20 AU. So I'm not too surprised by the fact that we're missing these objects. There may be something to be done here about the absence of TNLs with greater than 30 and high inclinations. That's something that I haven't done yet. Maybe we should at some point.
Okay, that's the last question. We need to keep going. Thank you so much.